Good morning. Thank you for coming to the talk. I appreciate it. So yes, as Nikki said, I work at IBM in what's now been rebranded as the runtimes team, right? So we work called the Java Technology Center for the longest time because we work on the Java implementation. We're now actually working on implementation of other languages as well. But today I'm going to talk to you about what we do in the Java space, and in particular how we use our knowledge of Java to bring to bear on Apache Spark stack. Let's not start with that. So just by way of a bit of a background, you may not be aware that IBM has got its own Java implementation, but that implementation is kind of derived from a lot of the open source code around Java. So we, as a company, license Java from Oracle, so we have the rights to all of the code which is put in there for the class libraries and for hotspot. The class libraries are pretty much the same as you get in OpenJDK or Oracle Java. But then we add in some of our own technologies. So if you sort of peel away the covers of an IBM Java implementation, underneath you would see parts of the class libraries which are kind of just a straight pass-through of what you get in OpenJDK. So things in the UI space, AWT and Swing, we don't have a lot of sort of business incentive to work in that space. So that's pretty much a straight pass-through. However, we have some enhancements in things like XML parsers and the security crypto libraries. That's some places where we can have some acceleration put in those places. So for example, we support hardware crypto cards in some of the mainframes. We've got special libraries that enable us to do that. So some special libraries in there. In the core libraries, in the lang and the IO and that sort of stuff, it's a bit of a blend, right? There are some places where it's exactly the same code. There are other places where we've enhanced it, most notably for platform coverage. So IBM ships Java on more platforms than any other company. So we do it on big mainframes, we do it down on little embedded devices. And so some of the changes that we need to make in the Java implementation are to accommodate that. And then I guess most notably down at the lowest level is our virtual machine is different. We have what we call the J9, which is just a project name, the J9 virtual machine, which is a completely different implementation of the interpreter, the JIT, the GC, and all those things, right? So that's been written to optimize the stack. And what we do is we ensure that the J9 virtual machine is generating code which runs very efficiently on Intel and on Power and on Z systems. And it does that by using some heuristics and optimizing all the way up the stack for the applications which our customers care about. So that's a bit of a background of IBM Java. But today I want to talk about the stack, which is Apache Spark. Now I've got a few slides in here about describing what Spark is, but I'd be interested in a quick show of hands. Who doesn't know what Spark is? Just a couple of people. All right, so I'm assuming that most people do, and therefore I'll go through the Spark section really quickly, and I apologize if you get left behind a little bit. But Apache Spark is this computing platform for handling very large data. And if you look at their architectural diagram, Spark is made up of a number of different components, all which are built around this core capability. Now, the core has the ability to draw in data from lots of different types of data sources. And once that data is in Spark, you can then manipulate it using APIs directly at the core level, and then a bunch of libraries that they've built upon the core to do things like streaming, graph analysis, that sort of thing. And there are APIs that come in depicted at the top there, so you can interact with Spark either using Java or Scala, Python, or R. But from my perspective, one of the interesting points about Spark here is that it all orients around that core implementation. And so whilst you're doing all these different operations and these different APIs, you're actually operating down on the fundamental capabilities that core provides. And that allows you to express your application very naturally. There are parts of your application where you want to do graph-type operations. You want to find relationships or distance between various types of data. Or perhaps you want to see your data like an SQL database, and you just want to see it in rows and tables. So at different points in your application, you can use the APIs that are appropriate, and it goes down to the core capabilities. It's always operating on the same sort of data underneath. Does that make sense to folks? So that kind of blend allows you to get a good variety of applications written in a very natural fashion. You then run your application on a computing cluster. And the computing cluster is made up of a master and workers. Now again, I'm not going to, because most people around here already know Spark, I'm not going to go into details of how these work. But the executors in the workers receive a copy of the application code. That's distributed out amongst the cluster. And then they're given tasks to do to achieve the overall piece of work, which has been described by your main application. And each of the workers in the cluster is given a portion of the data to work upon. Okay? Now that data is described as what they call an RDD, a resilient distributed data set. So you can think of it as an application programmer as just a huge collection of data that you can write your application and not, in theory, not really care about where that data is being partitioned across the cluster. In reality, what happens is as your application executes, those operations are constructed. They're then deconstructed at the point at which you need the result for the data. And the very large, huge collection is broken up into partitions of data. And each of those are given to an individual worker to work on, and the results are collated back again. So folks that know Spark kind of know that stuff already. But from my perspective, from a Java implementer's perspective, what I'm trying to do is ensure that Spark runs as efficiently as possible across the virtual machines that are on the cluster. So each worker and the master have got a copy of a virtual machine, and they all have an individual part of this task to complete and send the data back for the results to the end user. And getting that done as efficiently as possible boils down to two things in my book, right? One is how quickly can we move the data around the cluster so that everybody has got a piece of work to work on as quickly as possible, so there's no delay in shifting the data. And then once they've got that piece of data, how quickly can they crunch through the numbers, get a result, and be ready to send a result back to the master. Now, there are some points in your application where you're going to be bound by your computing speed. So if you have got data which can be processed by the workers independently, then the question is, how quickly can one worker transform that data from end to end to get a result back again? So if the records or the data points don't have a lot of interconnections, then you can process the data very quickly without having to depend on anybody else's intermediate results. The contrary to that is some applications where there is a lot of interdependency between the data. And there, you end up where you have to, what they call shuffle the data, that is, send the data between various nodes in the cluster. And there, you're probably going to be bound by the speed at which you can shift bytes over a network, right, rather than the computing speed. So let's have a look at a few things that we can do from the JVM perspective that are going to give us some enhancements. And I'm going to go through these four different areas that we sort of investigated running the Spark stack on the Java virtual machine and some of the lessons that we'd learned from that. And of course, the first thing that you do is you start to profile what your application is doing and seeing where it's spending its time initially. So this kind of comes under the general heading of compiler enhancements. Now again, I'm assuming that as a bunch of Java developers, we pretty much understand how Java works, but kind of very briefly, when the bytecodes start running, whether in a worker or in the master, they're going to start in an interpreted state in the virtual machine. So we're literally kind of doing what it is that the bytecode sequence tells us to do. After a while, then we start to convert those bytecodes into a machine code that's specific to the architecture that we're running on. And as we sample the application, so there's a sort of a stop the world and have a quick peek at what's happening on the stack at the moment, the execution stack, and we see the same method in your Java application being invoked over and over again, then we kind of figure, this is a hot method, right? This is something that we're going to have to spend more time compiling. And the JIT's role in life is to kind of compromise how much time it spends analyzing your application and generating as efficient machine code as possible, with balancing that time spent with the time that you will get back by running more efficient machine code, okay? So obviously, if you only run a method a couple of times, there's no point in doing a huge global analysis and optimizing the code for it. So it's only until you start to get up to the hot compilation levels where we're compiling it down into machine code And then we start to insert some of our own probes into the code to figure out, not only how often is this running, but what does the data look like when it's coming through here? How often do you go down the if rather than the else branch? And how many times does this loop typically run? And then we can use that profiling information to generate our best guess of how your application is going to run, start to do some heuristic optimizations about which branch you're going to take. We can unroll some loops and all the kind of standard compiler optimization techniques. And so eventually, you hope to get to a point where your application has been globally optimized using some usage patterns that we've gleaned from profiling the application actually running. And then we do other things which are purely speculative, meaning, although Java is a dynamic language, we're going to assume that things don't change based on what we've seen so far. But if they do, we're going to have to go back and undo some of those assumptions. So once we started profiling it, we came across things like this, which was a JNI call in the snappy compression libraries, where the whole purpose of this JNI call was to actually just do a mem copy, right? So there's some kind of setup and teardown around that mem copy. But essentially, we've got the overhead of a whole JNI call just to go down there and copy some blocks of memory around. And the problem with doing that is that once you leave the context of Java and you drop down into JNI, there's an overhead for doing that. It's an overhead in a couple of dimensions. The first thing is, when you're entirely in a Java world, we can set up the stack and the memory exactly as we want to see it for invoking methods, right? Once we have to call out to a C function, then we have to set up the stack and any registers, etc., for invoking C function calls. And so that kind of means that we have to rearrange some things that we had previously optimized. But kind of almost worse than that, we're blind to anything that happens inside a JNI call. So we can't see that down there it was just doing a mem copy, right? If that had been a system array copy or equivalent thereof, or call to unsafe, then we could have a look at that. We would know what it was doing. We could inline it into the method that was calling it, or we could make other optimizations to actually copy that memory across. There are other things like copying memory. So for that one, although it's doing a get array critical, on some VM implementations, and in fact in the IBM implementation, getting a reference to an array ends up copying that memory to a different part. And we do that in IBM so that we can continue with our GC implementation running. So I guess the message from this is, very judicious use of JNI. It's really kind of an interface into sets of libraries or capabilities which you can't get from Java. But this was one which kind of flagged up very early as being a problem. Another thing that we saw quite a lot of use of, and we got quite a good boost from, was, again, using some of those heuristics that I spoke about earlier. So today in Spark, there are a bunch of log infos that you'll see scattered around the code, which obviously logs some sort of a message to tell you what Spark is doing. And if you look at the implementation of log info, which is up in the logging trait, you'll see that log info, the check that it does is, is the log info enabled? And that's a check of a static Boolean variable. And so, most of the time it'll be set to false, which is fine. But we kind of have to check that every time because it's not a final. And there's some overhead in going over there and checking that. Now, an alternative way of writing logging like that would actually be to use a loginfo class, right? And to only load that class when you actually start to do some logging at that particular level. And what so the difference between those two things from a JIT implementation perspective is that we can start to use those heuristics because we can tell, obviously, when a class is getting loaded. We need to know that. And as we optimize the code and we know that the loginfo class has not been loaded, then we know that that whole operation there becomes a no-op. And so this these entire calls to the loginfo actually don't get compiled into any code whatsoever. The whole thing disappears. So that's obviously the most efficient code that's there. Now we've got the hooks in place that say that if you then turn on logging, right, and we start to load that class, then there are a number of places where our heuristic has been broken and we have to recompile things. And so any methods that include that would get recompiled and then the logging would start to work. So sort of hooking into some of the heuristics that the JIT uses really can help us to reduce the amount of code that we're running. And then just the coding style as well. So there are a number of places in Spark where there is heavy use of polymorphism, right? So it's methods that have got the same name but do different things. So they're in different classes. And when you abstract that out and then all of the calls are to the abstract, it means that from a compiler perspective, we have to, again, be speculative about which concrete implementation of that abstract class is actually going to get called. Not only that, but places where, methods that are doing essentially the same thing do it, but in a different order, slightly different order. And so, there are lots of examples where we saw this interruptible insert all, where in one case it's doing a map followed by a filter, and in the other case it's doing a filter followed by a map. And again, the problem with that is that if we're going to optimize the code, we want to see consistent patterns that we can recognize and generate very efficient machine code for. So once we'd done that, and we'd been through and we'd changed a whole bunch of these things, we actually found quite a nice improvement in Spark's runtime. So if you look at the graph here on the left-hand side, this is showing you the change in time between where we started, which is kind of the normalized version here. This is our Java 8 initial implementation, and I guess that's the fourth service refresh with some of these heuristic changes put in place. We're getting 1.35x speed up on some Spark benchmarks. And those are some breakouts there of the performance compared to OpenJDK 8. The one that's letting us down really is that Bayes call, where we're only running at 91% of OpenJDK, and that's because it's a very heavy use of JNI, that particular benchmark. So we have some ideas as how we can fix that, but for the moment, other things are looking pretty good. So overall, double-digit percentage improvement in performance. Likewise here for the Spark, the Databricks performance benchmarks across different size of clusters. So it turns out that about a 50 gig heap size is about optimal for the IBM Java implementation. And there we're seeing 130% advantage compared to other implementations. So that was tweaking the JIT to do a better job of looking at Spark. The other thing that we did then was kind of take a bigger picture look at where Spark was and some of the things that we could change. And obviously, if you're shifting data around in the network, then serialization becomes one of the overheads. So luckily, Spark has already got this framework in which you can write your own serializers and plug them in there. I guess they've changed. You can use the default Java serializer. You can use a cryo serializer. We actually have some of our own technology for doing serialization that we use in the orb today. And we thought we'd bring that to bear on Spark and see what the effects of that were. So some of the things that we optimized were just looking at some additional types that are specialized. So obviously you have very short sequences that you're going to send across the wire if it's a known type. Sharing object representation, meaning that if you have a sequence of serialized bytes, then you can have pointers back to existing instances rather than having to create a new one, which is fine, but we do have to watch out for that one because Spark operates in this very large data model across a cluster. One of the goals is that the clusters can operate independently. And if you have a serialization format that actually depends on other parts of the data by back pointers, then you end up sort of defeating that because you have to leap around inside the data. What you really want is a cluster to be able to go to any point in the middle of the data and just start to read from there without any other dependencies. And then, of course, very length encoding. We changed our implementation in a couple of places. So typically, if you want to maintain state as you're traversing your large object graph, you'll do that on the stack. That's fine unless you have really deeply nested objects. And in Spark, we did find, because these RDDs have got dependencies on other RDDs, et cetera, that there are some very, very deep object graphs inside Spark. And so we had to have this sort of hybrid approach where we'd start off using the Java stack to keep track of the depth, but then eventually you'd have to go to a state machine to figure out where you were. And after all this work, we ended up with kind of single-digit improvement performance by switching serializer, and kind of decided that for all that work, it probably really wasn't worth the effort that we'd put into it. And so, yeah, the goal is there to contribute all those little fixes back out into the open source project, but by and large, stick with the serializers which already exist. Okay, so let's look at some networking. One of the technologies that we've got in the IBM Java implementation is RDMA, which is the Remote Direct Memory Access. So a quick intro to that. Imagine you've got two separate machines here. We've got the node 1 and node 2, and they want to exchange some data. Well, this is your Java virtual machine, little box at the top here that's talking to the other Java virtual machine. And the data is it's either all in the Java heap, or it's sort of a direct byte buffer, which is maintained off heap. Typically, what you would do is go over TCP/IP to send that data, but that actually results in you having to copy the data down into the kernel space in your operating system, and then you go over the network interface card, over the network, and then back up the other side there. But what RDMA gives you is the ability to bypass this OS call here. So it gives us a couple of nice benefits. First of all, we can get a direct pointer to the memory which is contained in the Java space and pass that directly through an RDMA-enabled switch. So we work with Mellanox to do that. And then you can either go over Ethernet or over InfiniBand, and then straight back out using zero copy out into the node on the other side. And of course, when you do that, you get a couple of things. You get low latency, meaning the length of time that you actually wait between the sending the request and receiving it on the other side is significantly reduced, and also high throughput. That's the amount of data that you can send one after another is improved. So if we plot those two things on here, you'll see on the left-hand side, this is the throughput. And here I'm comparing TCP/IP as I increase the message size. I'm trying to send more and more data, and this is the rate at which I can do it using TCP/IP. RDMA is this graph here. You see it has much nicer characteristics for the amount of data that I can send. Likewise, over here, I'm plotting the latency against message size. And TCP/IP is pretty linear in this direction, saying that the length of time it takes to send and receive a message increases proportionally with the message size. With RDMA, it's linear, but it's way down here, so we see much better characteristics. When we bring that to Spark, Spark has got a communications infrastructure built around NETI, or NIO directly. We kind of looked at the NETI implementation. NETI itself has got some pluggable transports, and so by default you get NETI over NIO. So that's regular sort of Java sockets. One of the things that we did was to subvert, that is, take the Java NIO APIs and rewrite some of the implementation of that, so that if both sides of the communication were RDMA enabled, that the data would go over RDMA rather than TCP/IP sockets. Okay? So without having to change the application, they can still invoke NIO APIs, but the data would actually be going over TCP/IP, over RDMA rather than TCP/IP. So we plugged in that one. That was one that, the other thing that we were looking to do is to plug in some RSockets implementation, or some what we're calling the JVerbs. So RDMA natively uses verbs API implementation. We've got implementation in Java that wrappers verbs, and so a transport which goes over RDMA using verbs from NETI is probably about the most efficient that you're going to get. Now, the interesting thing was that once we changed the characteristics of this communication channel from the ones that we saw with TCP/IP to start using RDMA, it actually changed some of the more kind of fundamental algorithms up in Spark space. And so we have a team at IBM Research who've been working on the shuffle strategy, sort of deciding which block of memory to send to which worker based upon the faster communication that you're getting with RDMA, and that's showing some pretty good results as well. Okay, so let's put some of this stuff together. Obviously, if you're improving the networking, that's one which you want to consider for the shuffle-intensive benchmarks. So one in particular that we looked at was TCP/H benchmark, which is an SQL-based one. We're seeing 30% improvement in those operations, and with the page rank, 40%. And because we're not having to interrupt the OS all the time to get it to do some of our work for us, then the amount of CPU usage goes down as well. So we're seeing some pretty nice returns on that work. And then when you're looking to sorting very large hunks of data, so TerraSort is a standardized benchmark. We saw on this machine down here, IBM Java 8 on a 32-core machine with one master of 4 nodes. The time taken to sort a terabyte of data went down from 556 to 159 using that Java sockets over RDMA technology. So you see there's significant improvements in some of the performance by changing the Java implementation itself and not having to change the implementation up at the application layer. Here's another technology that is specific to the IBM Power architecture. It's called CAPI Flash. So CAPI is this coherent accelerator processor interface. Again, it's a similar sort of principle, really, that you're not interrupting the CPU to start doing some of the I/O work. And all of the benchmarks that we had been doing were based on flash drives anyway, right? So it was all SSD-based I/O. But the difference here is that once you're doing the I/O between the processor and the I/O kit, then you have to set up for a whole bunch of I/O before the application actually gets to do anything, and then strip down at the other side. And with CAPI, that whole setup and strip down is much reduced, right? So what we found was that it wasn't the overhead of the flash drive itself which was causing the problem. It was more the file system, right? And the file operations upon that flash drive which was causing the slowdown. So using this as a block I/O device, so we didn't have a file system installed on it, we're just storing and retrieving blocks of information, we were able to get far better throughput on storing our data, our intermediate data, out onto disk compared to putting it through a file system. So for Spark, the way we hooked this into Spark, there are a couple of places where we're doing storing to disk in Spark. Most notably, if you are processing a partition and you have more work to do than you can fit into memory, then Spark needs to page some stuff out, right? And it does that using these external append-only maps. There are more places in which we would like to apply this technology, but it's not yet pluggable in Spark, and would require quite a bit of work to rearrange Spark to allow us to plug this kind of stuff in. So we only did it in that one place where we're spilling the memory out onto disk for memory pressure during processing. The advantage of this is that it allows us to reduce the amount of working memory for each Spark node compared to when you have a file system that you're spilling to. So the use case here would be that you have all of your nodes set up in a cloud environment, and you're paying for your cloud by the amount of memory that it uses and the amount of CPU that it uses, right? You want to reduce the amount of memory footprint for your work cluster. And by using this CAPI Flash technology, as you can see here, the blue bars represent the performance when we're going to the disk, and the green bars represent the performance when going to the CAPI Flash drives. is that as we reduce the Java heap memory, we're getting better performance compared to disk, to the point that, I've just drawn this as a particular example here, an 8 gig JVM heap is performing about the same with disk as a 2 gig Java heap with Capi Flash, okay? So we can reduce the size, the in-memory size of a Spark worker and still get the same throughput by using the Capi Flash technology. Another cool thing that we work on is GPUs. So again, following the same sort of theme as before of offloading things onto I/O cards, security cards. We've got these GPUs which we ship as well, so let's try using those. Well, we have some technology already in the IBM Java implementation today which allows you to offload work to a GPU card. So if you get the IBM Java implementation and you do arrays.sort, what that will do is take a look at the array that you're trying to sort and figure out if it would be more efficient to sort that on the GPU rather than on the CPU. Now, there's a time cost to sending that data down to the GPU, sorting it, and then bringing it back, compared to just sorting it directly in the memory using the CPU. However, that cost sort of cuts over at around 30,000 elements. So if you're sorting more than 30,000 ints, floats, doubles using arrays.sort, then we're going to shift you down onto a GPU and sort it down there. So here, this is our little plot of increasing the length of the array that you're trying to sort on the CPU, and you'll see it sort of diminishes over time, the number of elements sorted per second, compared to a much nicer curve. And this is, that's a logarithmic graph, so it's kind of pretty impressive here. What happens when you copy that data down to the GPU, sort it, and then bring it back? So we're able to use that to do some large sorting if you've got a partition that's got a large piece of data, like TerraSort, for example, and you're trying to organize all that stuff. But there are more places in which we can do GPU optimizations as well. So that's an explicit call to arrays.sort that you've made from your application. What if we could tell that your application could benefit from GPU without you making it explicit like that? Well, what we do in the JIT, again, because we're looking at your code, we're doing the data flow analysis, we're looking at how many times you're going around a loop, and we're optimizing some heuristics based upon that. What the JIT can do is take a look at your expressions and determine whether that expression is better represented down on the GPU rather than in the CPU. And so as we go through that bytecode through the optimization, we will either code gen it down to the CPU or to the GPU. Now, it comes with some caveats, right? Because we are copying the data down onto a GPU, it's not just an extension of the Java heap, so we don't have all the sort of, the objects and object pointers and GC happening down on the GCU. We're just copying regular data down there. So an example of the sorts of things that we could move down onto a GPU would kind of look like this. And this is a bit of Java 8 code. So I've just created a range of integers of 0 to col's size. The key word here is parallel. So that tells us as a JIT that each of these operations can be done in parallel, which is what's going to happen down on the GPU. And then for each block, you'll see here there's just simple math. So there's divide and mod, there's multiplications, there's some addition going on. And so when the JIT compiles this code, it sees that this is a candidate for moving down onto the GPU. And so rather than emitting regular code, it actually calls out, runs it on the GPU, and brings it back again. Again, there are heuristics in there to determine when it's the right time to do that or not because of the overhead of copying down to a GPU. But there's also overhead of just doing things in parallel anyway. So what I've plotted over here on the right-hand side is showing you a comparison of parallel for each on the CPU, which is the red, and parallel for each on the GPU, which is the green. So as we have very small, and then this is a speed up here. So as we have a very small amount of data, an 8x8 matrix, it's faster to stay down on the, where do you find this? I click on the GPU actually. The auto SIMD is where we take a look at these and automatically use some of the single instruction multiple data characteristics of the CPU itself. So what would typically happen is auto SIMD is on by default. You would have this sort of a characteristic as your application runs on the CPU. This is where we've turned off automatic parallelization on the CPU. And then this is what would happen if you run it on the GPU. And because of the small size of the matrix here, there's the overhead of copying the data and then passing control, kind of like doing a JNI call down to the GPU and invoking a kernel down the GPU and then bringing the data back. So it's only when you start to see some relatively large matrices that you see the significant difference between doing that. But the advantage is this is just regular user code where we're making a decision as a JIT to do the optimizations, and it would run equally well on any sort of architecture. And there's a talk tomorrow by Adam in a lot more detail about GPUs, where he'll show how you write all that GPU code. The guys at IBM Research were looking at not only using GPUs for the low-level individual loop type optimizations, but doing some of the high-level things as well. So you remember way back at the beginning, I said there were some high-level APIs that people use for manipulating the data on Spark. Well, rather than boiling all those down to core capabilities, what if we intercepted some of these sort of machine learning type APIs and went straight onto GPU and got it to run on the GPU at that level rather than doing it at a low level? And so in this particular example, the example was to take a database of drug interaction data, so characteristics of different types of drugs, known interactions between two different types of drugs, and then use that to build a model, and then use the model to take drugs that you don't know how they interact and to then predict if they will be safe to take together. Okay? So in the first case, we're ingesting a very large amount of data from this drug bank stuff. They're sorted into large tables inside Spark. We then ingest a whole bunch of interaction that tells us which drugs are similar, which ones have some interaction which is undesirable. And then this is the model which is built. And then from that, we start to predict, given any two other sorts of drugs, what the problem would be if we were to interact between those two things. And the top line is running through those various stages just using the CPU. And then on the bottom, going through the same stages, but where we've done that model building on the GPU. And again, you can see a significant improvement on redirecting those machine learning calls to build that model from the sparse data matrix, running that on the GPU, and then presenting the information back to the user. So the user doesn't have to change their application code. They're still making Spark API calls, but in this case, we're intercepting it at a much higher level, and we're going down to the GPU, building the model, and returning it to them. So I'll give you a very kind of whistle-stop tour through a variety of things that we're doing here. We've, as a Java implementation team, we've tended to focus on that core level, right? How quickly can we process data? How can we change the heuristics of the Java virtual machine to do a better job for the types of application that we see Spark being driven? And we focused on the networking. How quickly can we shift data around between those two things? We do that in the context of not only the processors that we've got and the hardware that we've got, but also in terms of the, what was I going to say? Yeah, in terms of the context in which Spark is used. So in terms of cloud, for example, right? So we have cloud as a service on a whole bunch of providers. So looking at things like how, what's the effect of reducing the amount of memory that you give to Spark and how we can optimize for that as well. We push all of our changes that we're making to Spark out into the open source project. So you'll see a bunch of us working out in the project there, making commits. or rather making pull requests for the committers to take. We don't have any committers in our runtime team, although we do elsewhere. And there's a whole bunch of other things which I didn't really have time to talk about. So we've been discussing about how Spark, because it's managing these large pieces of memory, can interact better with the GC algorithms that we've got, how we can change object layout. We use FPGAs for hardware compression, which I didn't get time to talk about, and so on and so forth. But we put out our builds of Spark plus the IBM Java implementation that's best for running Spark on DeveloperWorks, and that's kind of the link for going to get it. So that was all I had. Is there any questions? I think we do have some time left for questions. Anybody? Kirk? Go on. You can have a microphone, but we won't turn it on. I can hear you.
In my profiling of Spark applications, the biggest offender, performance offender I found has just been simply index creation.
Meaning, what part of index creation?
Well, just creating all of the indices. There's all these like little small index objects that tend to be created.
The objects, right?
Sorry?
Go ahead.
Yeah. So, so far I actually haven't seen you mention that, or if you have any ideas of how you might cope with that. It's certainly it's a frequent enough event that it does actually, well, at least in OpenJDK, present what I call a considerable performance impediment in the applications. Yeah, I know indexes are necessary, but
yeah.
And could you possibly comment on the use of value types in helping these types of problems?
Yeah, so, okay. So with regards to indices, I guess we may be working at a slightly lower level in terms of not going up into the application and poking around too much into how they've chosen to implement a lot of that stuff. Certainly, you know, they do create a lot of objects. There's a whole bunch of stuff happening in Scala land as well, which we noticed, which could do with some optimizations as well, or at least, you know, don't do a great job for our JIT implementation. Value types, well, you'll be familiar with the Project Tungsten work that's happening, or has happened, I guess, at Spark, where they've kind of made the decision to manage a lot of their memory themselves directly outside of the Java heap. I suspect that will get them so far. Again, it's maybe I'm just saying this as a Java guy, but I think we could do a better job by managing that directly on the Java heap.
I think structured object layouts would actually be much better than going off heap.
Exactly, yeah. And so, you know, once they start to get value types, then perhaps the balance will change a little bit. And you know, once they start to push Project Tungsten to a point where they're having to manage complex life cycles of objects, they're looking at NUMA stuff that, you know, we already do in GCs. As soon as they start dabbling onto GC, it's one of those areas that sounds easy, but it's not, right? There's years and years, as you know, there's years and years of research around efficient GC, and I think they would do well to come back to leveraging a lot of that stuff. Any other questions? No? All right, thank you very much for your attention.